All right, hello class. Mr. Pettibone here. Hope everyone's doing well. This is our second day of complex numbers. Next week we're going to move on to the item that you guys really wanted to study, which was special relativity. Next week we're only going to be going 4 days a week. I don't see why we have to do 5 days a week. So we'll just do 4 days a week. Give you a little update on my blade that I have been forging. I put a handle on it yesterday, and pretty much done. I just need to put a better edge on it. So you can see yesterday it was about the length of a piece of paper, and now it's slightly longer than a piece of paper because it was too thick, and so I hammered it down to thin it out. And then I spent a lot of time filing it to make sure, like, I filed these finger holds. And then I drilled holes. This part of the knife that the handle attaches to is called the tang. So I drilled holes in the tang, and I got these little pieces of wood, and I cut those to shape. And then I got like brass cylinders, and I put those through, and I super glued it all together. So I think it's pretty cool. This was a railroad tie, so it definitely could be sharper. I cut an orange up with it, and that worked pretty well, but it's definitely not razor sharp, so I'm going to work on probably sharpening it today. Yeah. Let's see, who else is here? Hey Fu, hey Justin, hey Zach, hey Nick, hey Rowan. All right, so let's get down to it. And today we are going to learn about what's called the exponential form of complex numbers. So the exponential form. And the exponential form of complex numbers is really useful. And it's all based on the following theorem. So the theorem is e to the I theta. So think about that. We're doing e to a complex number, okay? Equals cosine of theta plus I times sine of theta. Okay? So that is a theorem. It's called Euler's theorem. And that's what the exponential form of complex numbers is based on. So if you wanted to prove this, I'm not going to do the proof because not everyone is in Calc BC. But the idea is you use the Taylor series for each of these things. All right. So for example, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc. And then cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. And sine of theta, or sine of x, is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So if you use these Taylor series definitions of the functions, and you combine these two, you multiply this one by I and you add them up, you find that you get the Taylor series for e to the I theta. Okay? So that's the proof. I invite you to work out the details on your own. So what that means is you might recall that the polar form of a complex number is r times the quantity cosine of theta plus I times sine of theta. So, but notice that this is just e to the I theta. So the exponential form of a complex number is r e to the I theta. Okay. So this part is called the modulus. So recall it's the distance of the complex number from the origin. Okay. And theta is sometimes called the argument. It's the angle of the complex number in radians. Okay, I use radian. This theorem is true where the angle is expressed in radians. All right. Complex numbers make it really easy to multiply complex numbers to. So let me show you how that works. What if we have z1 times z2? Okay. z1 times z2. So that would be r1 e to the I theta 1 times r2 e to the I theta 2. Okay? So this is just 4 things multiplied together, so I can use the commutative property of multiplication to rearrange this. So I get r1 times r2 times e to the I theta 1 times e to the I theta 2. Okay? And notice when you take two exponentials and you multiply them together, the exponents add. So this is equal to r1, r2, e to the I theta 1 plus theta 2. Okay? So that makes it super easy to multiply complex numbers. Okay? It's kind of interesting. It says, so what this says is that when you multiply complex numbers, their moduli multiply together and their arguments add. Okay? So, for example, what if I multiplied 2 complex numbers? Okay. Maybe this is z1, and maybe this length right here is 2. Okay. And then z2 is right here. And let's say this has a length of 3. So if we were to multiply them together, Justin is right with his response to that question. I just saw it. If you were to multiply them together, the resultant complex number is going to have a magnitude of 6, because that's 3 times 2. We're multiplying the moduli together. And then the angle is going to be this angle plus that angle. Okay, so I got to kind of add this angle onto that angle. So that gives almost a 90-degree angle. And it's got to be about this far away. So this one would be Z1 times Z2. Okay? So that's sort of the geometrical meaning of multiplying complex numbers. Of course, if we do the complex conjugate of a complex number, it means you replace I with negative I. So you have r e to the negative I theta. And you can see that that's basically taking the angle and making it negative. And you might remember yesterday I talked about how complex conjugation is reflecting the complex number in the across the real axis. And so you can see that if you make the angle negative, it does just that. Okay. So that would kind of be like, this is a positive angle, then the negative angle would be this. So you get the same modulus, but opposite angle. Okay. One thing about the argument is that it's only defined up to 2 pi. Okay. So, r e to the I theta is equal to r e to the I theta plus 2 pi. Because that would mean you went around the circle an extra time. So, adding 2 pi to the argument does nothing to the complex number. We can also raise complex numbers to powers. So what if I wanted to do z to the k power? All right. So if I wanted to do z to the k power, this would be r e to the I theta to the k power. And so that's equal to r to the k e to the I k theta. So you can see that the modulus gets raised to the power k, and the argument gets multiplied by k. All right. We could also divide complex numbers really easily. Z1 divided by Z2. That would be R1 e to the I theta 1 over R2 e to the I theta 2. Okay. And you might know that when you divide by something, it's like raising it to the negative 1 power. So I could take this e to the 1 over e to the I theta 2, and I could write it as e to the minus I theta 2. Like that. And then that's R1 over R2 times e to the I theta 1 minus theta 2. So when you divide complex numbers, their arguments subtract, and their moduli divide. Okay. Let's do a little example. How would I convert a complex number into exponential form? Okay. Hey, Bugger, stop digging, please. He's digging his dog bed. Why don't you come over here? Come here, Bugs. Buggers. Come here. Come here, Buggers. Come here, all the way. He's an 11-year-old boy now. Yeah, good boy. Why don't you just sit next to me? Okay, he's going to sit behind me. So what if I wanted to convert the complex number z equals, let's say, 10 plus 4i into exponential form, okay? So first of all, I need the modulus, okay? And so that would be square root of 10 squared plus 4 squared. All right. And that gives me 10.8. And then thinking about the argument, well, this complex number has a real part of 10 and an imaginary part of 4. Okay. So we want that angle right there. That would be the argument. So that's going to be inverse tangent of 4/10. And my calculator is set in degree mode, so I want to convert that to radians once I'm done. So 21.8 degrees times pi over 180 gives me, so theta equals 0.38 radians. Okay. So we could write this complex number as 10.8 e to the I 0.38. So that would be converting it into exponential form. Okay. So what I'm going to do now is I'm going to show you some cool stuff. Okay. What if you can use complex, you can actually define all the regular functions that you know about for complex numbers. Okay, so I'd like to show you some of that. For example, what if I took this really weird combination? Okay, what if I took e to the I theta minus e to the minus I theta over 2i? Okay, so what if I found, if I just computed that combination? So I'm going to use Euler's theorem twice. Okay, I'm going to use it here and here. So if I use it in the first term, I would get cosine of theta plus I sine of theta. Okay, and then I have minus minus cosine of negative theta plus I sine of negative theta. All right. And so now we're going to use the fact that cosine is an even function. Okay. So cosine of negative theta is just cosine. And then sine of theta is an odd function. So this becomes cosine of theta plus I sine theta minus cosine of theta minus I sine of theta. So I used the fact that sine is an odd function and cosine is an even function. Now you can see that the cosines are going to cancel each other out because I have cosine minus cosine. Okay. And then the sine terms are going to add together because you have negative, negative. So you get 2I sine of theta over 2I. So you just get sine of theta. So sine of theta can be written as e to the I theta minus e to the minus I theta over 2I. Similarly, it's possible to show that cosine of theta is equal to e to the I theta plus e to the minus I theta over 2. Okay? So this allows you to do some really weird stuff. So for example, what if I wanted to know, what is the sine of I? Well, if you just do your normal way of thinking about things, you know, this doesn't make any sense because I isn't an angle, right? But once you have some knowledge of this formula, you can actually say what this is equal to, okay? So this would be equal to e to the I times I minus e to the negative I times I over 2I. So I squared is negative 1, so we get e to the negative 1. Negative I squared is plus 1, so we get minus e to the plus 1 over 2I. All right. So that would be, yeah, so that's what it's equal to. That's a complex number. It's a weird complex number. Okay. You could even define things like logarithms of complex numbers. So what if I wanted to know, what is the natural log of z? Okay. Well, that would be the natural log of r e to the I theta. Okay. Now, these are two things multiplied together, and when we take the log of things multiplied together, they add. So this is natural log of r plus natural log of e to the I theta. Okay. Now, natural log is the inverse function of e, so these two cancel each other out, and I just get e to the I theta. Or I just get I theta, excuse me. So you can take the natural log of a complex number. So I think it's pretty cool. I'm going to bust out a second piece of paper here. We could compute. Have you ever thought about what is I to the ith power? What is that equal to? Well, what we can do is, if we think about where is I on the complex plane, okay, I has an imaginary part of 1 and a real part of 0, okay? So if we think about this, it's a distance 1 from the origin, and it's at an angle of 90 degrees. Don't you do that. Bad Ivy. Meow. So we can actually write I. I has a modulus of 1, and it has an angle of 90 degrees. So we can write I as e to the I pi over 2. Okay? All right. So I is equal to e to the I pi over 2. So I to the I would be e to the I pi over 2 to the ith power. So see how we have I squared, which is negative 1. So you have e to the minus pi over 2. So that's I to the I. It's kind of cool, I think. There's another really famous formula. What if we think about I don't have a cat, but my friend's cat is. I'm cat sitting right now, so my friend's cat is over, and he's scratching the furniture. Let's think about negative 1. Okay, negative 1 is over here. Negative 1 has a real part of negative 1 and an imaginary part of 0. Okay, so what's the angle here? This angle is an angle of pi. So it's a distance 1 from the origin, and it has an angle of pi. So negative 1 can be written as 1 times e to the I pi. Okay? So negative 1 equals e to the I pi. This is sometimes written as 0 equals 1 plus e to the I pi. And people attach all kinds of profound meanings to this because it has, think about this equation, it has all of the fundamental numbers. It has 0, it has 1, it has e, it has pi, and it has the imaginary numbers. So this is a very beautiful equation made out of all the fundamental numbers that you've learned about throughout school. Okay? Trying to think what else I can show you. I can prove angle addition formulas using complex numbers. Watch this. Check this out. What if I take e to the I theta 1 times e to the I theta 2? Okay? So on the left-hand side, I'm just going to straight up multiply these. I'm going to use the properties of exponentials. So this is just e to the I theta 1 plus theta 2. Okay? On the right-hand side, I'm going to expand. I'm going to use Euler's formula. Oops. Okay? So let's FOIL this out. Okay? So I have first cosine of theta 1, cosine of theta 2. Outside, I sine of theta 2, cosine of theta 1. Inside, I sine theta 1, cosine of theta 2. Last, I times I, sine of theta 1 times sine of theta 2. So negative sine of theta 1, sine of theta 2. All right? Now I'm going to collect the imaginary terms, and I'm going to collect the real terms. So cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2 plus I times sine of theta 1 cosine of theta 2 plus sine of theta 2 cosine of theta 1. Okay? Now, on the left-hand side, I'm going to apply Euler's theorem again, only this time, see how I've combined the angles. So I have cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Now, the only way that two complex numbers can be equal is if their real parts are equal and their imaginary parts are equal. So the real part of this has to be equal to the real part of this. Okay? So that means that cosine of theta 1 plus theta 2 is equal to cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2. So we proved the angle addition formula for cosine using complex numbers. Similarly, the imaginary parts have to be equal, so that means that sine of theta 1 plus theta 2 is equal to sine of theta 1 cosine of theta 2 plus sine of theta 2 cosine of theta 1. So I think that's kind of neat. I like that. I'm trying to think of what else I can show you. A complex number. So I'll show you one more thing and then we'll be done. What if I have a complex number with a modulus of 1 and an argument? An argument is also sometimes called a phase that depends on time. So what if I have z equals e to the I times 2 pi t, for example? Okay. So this is a complex number that depends on time. So let's think about where it's going to be in the complex plane. All right. So if we think about it, it's always going to be a distance 1 from the origin. So here's 1 because it has a modulus of 1. So it's basically going to lie on this circle, but the argument is changing. Okay? What is the argument at time 0? The argument is 0. So here's the complex number at time 0. What is the argument of the complex number at time 1/4? What if t equals 1/4? Then it would be e to the I pi over 2. So it still has a modulus of 1, but its argument is now pi over 2. So this means that it's moved to here. Okay? And then what about at time 1/2? Now its argument is pi, which means it's moved all the way over to here. And then similarly, you can show that when t is equal to 3/4, then it's right here. So basically, as time goes on, what this complex number does is it just goes around the unit circle. Okay? So when you have a complex number that depends on time and it's whipping around like this is sometimes called a phasor. Okay? And phasors are extremely useful when you're talking about circular motion, simple harmonic motion, that kinds of things. it turns out that a lot of the equations that we learn about things, simple harmonic motion, for example, can be greatly simplified if we expand it to complex numbers. I'll show you one more thing, just because. What if I have two complex numbers in rectangular form? So I have v, and I'm going to write it as vx plus I v times vy. And then I have w equals wx plus I times wy. And what if I multiply them together? vw. Okay, that's going to be vx hang on a second. I think I want to do vw star. That's what I meant. vw star. So v times the complex conjugate of w. So that's vx plus I vy times wx minus I wy. Okay? So foiling, I get vx wx. Outside is going to be minus I vx wy. Inside plus I vy wx. Last is going to be plus vy wy. So now collecting like terms, collecting real numbers will give vx wx plus vx wy, or vy wy, excuse me, plus I times vy wx minus vx wy. All right. And so why is this interesting? Well, if we thought of these as vectors, this is actually v dot w, and this would be the cross product of the two. Okay, so this would be vx cross w, or v cross w. So complex numbers, in addition to somehow doing simple harmonic motion, they also somehow have cross products and dot products in them. So anyways, I hope that once you see and they also have vectors in them. Remember from yesterday. So it's complex numbers somehow have all of mathematics somehow smushed into them. And you find these like really surprising relationships between different areas of math that you might not have thought were related when you introduce complex numbers. And in physics, you have something that you thought was, really complicated, and once you frame it in terms of complex numbers, it becomes all of a sudden really clear what's happening. And so if you learn about complex numbers and you're going to go into any kind of STEM field, it's really useful to know about complex numbers. All right? So that's the moral of the story. I'll see you Monday, and we'll be talking about special relativity. Have a great weekend.